Hi there, and welcome to episode 6 of the Geology 101 video series. I'm Geology Professor Shawn Willsey. Thanks for joining me today. This is a video series, Geology 101, or Physical Geology, where we go through just the basics of geology. So if you're new to geology, haven't had any formal coursework, or maybe you had a class years ago and you're looking for a refresher or anything in between, then this is a great series for you. This is the place to be. This course is modeled after, these videos are modeled after my college course that I teach. The lecture and the curriculum is basically the same, and the only thing missing here are the labs and the field trip components of the course. But for the most part, you can supplement a lot of that material by watching a lot of my other videos, which include field trips. Others involve more lab activities like rock and mineral identification. So thanks for joining me. As always, you're welcome to support the channel. There is a PayPal link and a Venmo link under the video description, or you can click on the thanks button to the bottom right of the viewer, and that is another way that you can support the channel and my efforts at putting together these geology education videos. So thanks so much for your time and your support. Let's get right into it. We're going to wrap up our discussion of plate tectonics with just one more concept related to plate tectonics, and then what we'll turn to in our next episode is starting looking at earth materials. Especially next time we'll look at minerals, and then we'll piggyback onto that and go through all the different rock types and rock processes. So this last little topic I want to cover here is important, but it is not technically part of plate tectonic theory. So let's make sure we put a line in the sand between what we've covered previously with the other episodes, which discuss plate tectonic processes, which is a scientific theory, very robust. It's been tested repeatedly. It's on very solid ground in terms of being an actual process that we know works, although we don't know all the intricacies of how it works. And now we're going to shift gears slightly to another concept, or better, I guess it's better called a hypothesis, that's related to plate tectonics, but is not on as solid footing as classic plate tectonic theory is. And so this is this idea of hotspots. Basically, we've talked about plate boundaries, and that some plate boundaries, specifically divergent boundaries and subduction zones, are places where we see many of the Earth's volcanoes. And that's true. But we also have a few places that are somewhat anomalous, where they are nowhere near a plate boundary, and yet we have very active volcanic activity. The Hawaiian Islands is a good example of that, with the big island of Hawaii being the premier example. It's the middle of the Pacific plate, and yet there's this very active volcano that operates underneath the big island of Hawaii. So these ideas, hotspots, they're volcanic areas that are fed by anomalously hot material from the mantle. We'll get to that. These things called mantle plumes. Some of them are actually on plate boundaries, like in Iceland, and you can see maybe a few other of these red dots across the globe here, but a lot of them are independent of plate boundaries, not necessarily tied to or linked to any plate boundary. So as we get into this idea of hotspots, remember this is Geology 101 course, and I will present the very simplified model of hotspots. But let's be very clear here that this classic model of hotspots is overly simplified. It has been shown with research to have a lot of flaws in it, doesn't seem to work everywhere, and so we haven't totally figured out some of these locations and exactly what's controlling their volcanic activity, but it's a much more complicated process than what I'm about to present. So please realize that this is a very simplified view, but this is a good place to start, right? Geology 101, we're not an advanced tectonics class, so let's just proceed with that understanding in place here. Okay, so the idea here is we have these plumes of hot rock that rises from deep within the Earth. And we think that actually takes place right near the core mantle boundary. There's some thoughts that it's in the mantle without being anywhere near the core, but nonetheless, this diagram here shows the core mantle boundary being the location where these anomalously hot regions of rock. You might think of these as magma, but I think that's probably not the right way to think about it. Just let's think of it as hot rock that is maybe partially melted, but not completely, and is also buoyant. Okay, so it's hot, and so it can rise up through the mantle, and that can have a head at the leading edge, this big kind of bulbous area here, and then that's fed by this sort of chimney-looking feature here called the tail. As that reaches the Earth's surface, if we go to the middle diagram, that can eventually impinge upon the lower end of the crust. This is actually the plate, right? So this is the crust in the upper mantle, the lithosphere, and that can eventually trigger melting and magma that starts to rise through that crustal material, and eventually that can pool up. In this case, they're showing it on the ocean floor, which is where many hotspots are, but that can eventually produce a big outpouring of lava and volcanic material that in this case we might call a flood basalt. And then over time, because the lithospheric plate up here, the crust is moving, that will in this case move off to the left. And as we just have sort of the rising tail portion of the plume, we'll have a series of volcanoes that get older in one direction and younger in another direction. So this is a classic idea of these hotspots. Here's a different version of the diagram, looking at a little bit more specific area, looking at Hawaii, which we'll spend a little bit of time on. So here's the various islands of Hawaii. Starting out in the northwest here, let's start with Kauai, which is around 5 million years old. This MA is millions of years ago. It stands for mega annum. Oahu, which is about 3.5 million years ago. Maui, a little older than 1 million years ago. And then we finally arrived to the southeast at the big island, Hawaii, which is less than 1 million years old, and which of course contains at least 2, if not 3, active volcanoes. Kilauea, which has been erupting on and off for quite some time, and we recently had an eruption in 2022 of Mauna Loa, and a big eruption there in the 80s. We expect it to erupt again sometime in the future. So what you can see with the drawing here is you can see the mantle plume coming up, and the mantle plume currently is stationed directly beneath the big island Hawaii. But what's happening is the plate is still moving off, in this case, to the left or to the northwest. And so that changes the location of these volcanoes over time. So if you drag this thing backwards, you can envision that Maui used to be above the mantle plume and the hot spot. And Oahu, 3.5 million years ago, was above the hot spot and the mantle plume. So what this model or this hypothesis predicts is that you should get a series of volcanic features, in this case islands, that get older in one direction, in this case to the left, or in the other direction they get younger. The composition should be pretty much the same. So if you go sample the rock, their chemistry should be the same. And this would be the consequence of this classic simplified mantle plume hotspot idea. Let's go ahead and check out how this looks with a couple animations here. And so here's a simple animation showing the general idea. So what we have here is the mantle plume right there in the middle. This dark red area down low at the bottom of the diagram, this would be the asthenosphere. This brown layer would be the upper mantle or the lithospheric mantle. The orange would be the ocean crust, and the blue, of course, is the ocean itself. So if we go ahead and let this roll forward, we can see in this case the plate's moving to the right, but the hotspot stays fixed. It doesn't move. That's the model anyway. You can see the magma working its way to the surface, eventually forming a pile of volcanic material that rises above the ocean to form an island, but that island gets dragged off the hotspot. The magma from the mantle plume remains active, and so that eventually rises back up through that plate that's moving above it, and it feeds another volcano. So here's our next volcanic island being created, and then the process continues. So the idea here would be that these volcanoes and these islands are no longer volcanically active. They're probably getting smaller over time as the waves pound on them and erosion takes place. And then we get this final one right here. So we get a sort of progression of these islands over time. Let's look at just another quick another animation that shows this. In this case, I think we'll see the plate moving to the left here, but here's the mantle plume on the right side of the diagram. Here's our rigid crustal plate. There's the ocean, and you can see the magma rising over here in this area. So let's go ahead and let that one roll. There's the magma coming up. Eventually it builds up enough volcanic material that it forms an island. Okay, but the plate keeps moving, and the weight of the volcanic island actually pushes down on the plate. That's important in the area of Hawaii and other places as too. So we actually get this sort of flexure here. And now they're just speeding everything up so that you're getting more islands, again, getting older in one direction, younger in another direction as things are carried away from the hotspot by the movement of the plates there. So that's the general idea. That's what the model predicts. If we switch gears and look at Google Earth, and let's stay focused on the Hawaiian Islands for a while, the progression of volcanic islands and seamounts or submerged islands in the Hawaiian and Emperor Seamount chain is just beautifully displayed here on Google Earth. So you can start here with the modern Hawaiian Islands. You can see the big island here, go to Maui, work your way up the chain, but then you can continue off to the northwest. Now there's not a lot of islands here. A lot of these islands are submerged, but you can see with the imagery here to the seafloor where these islands used to be. So these islands have subsided. They have been beat up by erosion from the waves and the rain. A few of these barely stick up, you know, and form these things called atolls, just these like reefs that fringe what's left of the island here. Some of these were critical, like in World War II, for landing bases and military bases in the Pacific. But you can see this progression continue up to the northwest. There's an interesting thing that happens right here where it changes direction. This is what's sometimes called the elbow. And then it starts with more of a northerly progression, but eventually you lose this chain of seamounts as we approach this subduction zone, this trench here up near the Kamchatka Peninsula of Russia and off the Aleutian chain over here. The other interesting thing is we've looked at the Hawaiian Emperor Seamount chain is there's a nice, fairly consistent progression of ages. So the rocks here are brand new, less than 1 million years old. They get progressively older as you work your way up the Hawaiian Island chain. And then even if you go out into the Emperor Seamount chain here, the islands or seamounts get progressively older all the way till you get up into this area here. And so what that indicates is that, and they all have the same chemistry too, so it's indicative of a similar process. Whatever's formed the Hawaiian Islands today is also responsible for creating these other seamounts and other islands here in the chain. And then of course, you know, again with this simplified model in mind, we can predict what will happen in the future. The present island of Hawaii will be dragged off of the hotspot. It will move to the northwest, sort of move into a position where Maui is, and then there will be a new island or a new volcano that emerges in its place, because this is where the head of the hotspot or the mantle plume is coming up right here. So as long as that process continues and the plates continue to move, which of course they should, we should expect to find a chain of islands at this location in the Pacific for quite some time. But it might not be a good real estate venture for you in terms of very long-term real estate ideas to purchase any property like on Kauai, let's say, because as this island gets dragged further and further away from the hotspot, as it gets older, it's going to subside, it's going to sink. The sheer weight of it is going to cause it to collapse lower and lower and sink. The waves are quite fierce in this part of the Pacific Ocean. They get a lot of rainfall, and all of those combined effects are transpiring to eventually create it or turn it into a seamount, which is a submerged island here. A couple other cool things about Hawaii is there's a nice, so the rocks get older to the northwest and younger to the southeast. We've mentioned that. There's also some interesting things when we look at the topography. So if you look at the topography, let's say, of Oahu, and I don't know exactly what the high point is here, but if we just kind of scan around, you know, I'm guessing maybe 3,000–4,000 feet, something like that is the highest point on the island. If we move over to Maui, the high point here is Haleakala, which is over 10,000 feet in elevation, so a very high mountain that sometimes gets a little dusting of snow on it. And then if we finally leave Maui and head to the Big Island, this is where we can find mountains like Mauna Loa and Mauna Kea that rise over 13,000 feet. So the summit of Mauna Kea is something around 13,700 or so feet above sea level, which is pretty remarkable. Why is this island the highest among the whole chain? Well, it's sitting right over the hotspot. It's very young, it's thermally buoyant, but eventually as it gets dragged off the hotspot, the elevation of these mountains will get lower and lower, just like we see with these older islands in the Hawaiian chain. So hopefully that's a little bit helpful there. Okay, so let me take you back to the PowerPoint to wrap this up and show you just a couple more things. And we'll do a quiz question here at the end as well, for those of you that like assessments. So here we have the hotspot. We've talked about that. Kind of a blurry photo here. Apologize for the low quality, but this shows the actual ages of the rocks in the Hawaiian chain. So again, these are in millions of years ago. So less than 1,000,000 years on the Big Island, around 1,000,000 years Maui, 2 to 3 or so on Oahu, 5 at Kauai. But then we can continue that trend on the rest of this part of the diagram here. Necker Island's around 10 million years old. A lot of these are seamounts, but you can see the ages: 12, 20, Midway, 27. Around the elbow, it's around 43 or so, 43, 47 million years old. And then continuing up the seamount chain where it gets close to the Aleutian Trench, it gets close to 60 or so million years. So that tells us that this hotspot, this plume of magma and hot rock, has been operating for at least 60 million years and probably longer. Why don't we see anything older than around 60? Well, all this material gets subducted or pushed beneath into that trench that lies up here. So it could have been operating a lot longer. We just don't have any evidence because all the seafloor crust has been consumed beyond this point here. Okay, so that's the idea with hotspots. Pretty simple again, but I want to point out it does have its flaws. It's the subject of quite intense research, and hopefully at some point we'll figure it out a little bit. There are places where the hotspot model seems to work pretty well. And in Hawaii, that's generally true, but there also are some little flaws with it in terms of the trajectory and the speeds and some other things. So there might be some other factors and processes going on there. But let's look at another location, and let's use this as our little assessment question here. So what I want you to do is, well, let me explain the diagram and then I'll explain the question. So this is a diagram of the northwestern part of the United States. So here's Idaho. I'm located right here in Twin Falls. This is where I live and work. And across southern Idaho and other adjoining states, there is a progression of volcanic rocks that all have this similar chemistry. And you can see the ages of the rocks in millions of years here. So the McDermott volcanic field, right around 16 million years old. The Oahe Humboldt field is anywhere from 15 to about 13. Bruno Jarbidge, Twin Falls, Peekaboo, Heisey, and then up to Yellowstone. So this is the Yellowstone hotspot track. Yellowstone is also another hotspot. It's not on a plate boundary, and it seems to be fed by the volcanic material there seems to be fed by a mantle plume. This one's a little different though. Instead of being out in the ocean like most hotspots, this one's actually on land, which makes its volcanic eruptions much different. And that's a subject we'll get to when we get to igneous rocks and volcanoes. So I'll just kind of put a pin in that one for now. But you can see the ages of the different volcanic regions. You can see on the map sort of their progression. And I put a little compass rose down here in the bottom left corner to remind you, northeast, southwest. And what you want to do here, here's your question, is using just the most classic simplified hotspot model that I presented here, which we know has some flaws in it, but let's just go with it for now. And using the data we see on this map, can you say, based on this data and what you understand about hotspots, which direction this plate, the North American plate, is moving? So is it moving to the northwest? Is it moving to the northeast, to the southwest, or to the southeast? Which way is the plate moving based on the hotspot model that we've talked about? So I'll go ahead and pause here for dramatic effect. You maybe want to pause the video while you maybe do a sketch or think about this or have a conversation with a friend, whatnot. Okay, so I've given you some time there. And now we'll go ahead and reveal the answer. So remember, in the classic hotspot model, the hotspot is fixed. It doesn't move. What is moving, of course, is the plate is moving over the top of it. And so what we have here is we have a progression of ages that gets younger towards Yellowstone and older as we move to the southwest. So hopefully you at least figured out it has to either be southwest or northeast, somewhere along this trajectory here. One of these two directions has to be the answer. And that's true. It is one of those two. So it is either B or C. But what is the right answer? Well, if the hotspot stays fixed and the plate moves over it, over time we should get younger and younger volcanoes opposite the direction that it's actually moving. So the volcanoes are younger to the northeast. That means the plate is actually moving to the southwest over time. So the correct answer there was C. And I think this is something I talk about a lot when I take people on field trips. I think it has some interesting implications. For example, if you've been to this part of southern Idaho, where I live here in Twin Falls, it's kind of a desert, lots of sagebrush, fairly low elevation. If you've been to Yellowstone, of course, very different scene. Big lodgepole pine trees, high elevation. It sits on the Continental Divide. Abundant wildlife, lots of water, lakes, rivers. There used to be glaciers that covered it. But geologically, it's all tied to the same process. And so Twin Falls, 8 to 10 million years ago, looked a lot like Yellowstone. It was higher topographically. It was on the Continental Divide. It probably had abundant wildlife, although we don't have direct evidence for that. It definitely did have rivers and streams radiating and flowing away from it because it was the high point. And then what's happened is, as Twin Falls has moved off of the hotspot to the southwest along with the North American plate, the heat, that thermal buoyancy caused by the hotspot, that's been taken away largely from Twin Falls. So the area has subsided to a large degree. And that actually is what forms this valley here through most of southern Idaho called the Snake River Plain. This low area, this valley that runs across this portion of Idaho exists because it's in the wake of the Yellowstone hotspot. The other fun implication to talk to people about is like, well, if this process keeps going, if the plate keeps moving to the southwest, the hotspot stays active, what will happen into the future? And that basically means that in the future, let's say 8 to 10 million years from now, what will the Yellowstone National Park region look like? Well, it'll look a lot like Twin Falls, Idaho. It will be lower. It will have drier, more desert-type vegetation, not as much water, probably a different ecosystem in terms of plants and animals. And so it won't look anything like the current Yellowstone National Park that we all know and love. And so where will this hotspot be in the future? Well, it'll track through south central Montana and into eastern Montana. And then eventually it will be off the map here and up in Canada, which is kind of crazy to think about. But that's more or less the fate of the Yellowstone hotspot moving forward over time if this hotspot stays active and if the plate keeps moving the way it has. So anyway, that's just a fun way to wrap this up. Thanks for your time. Hope you enjoyed this episode of Geology 101 video series with me, Shawn Willsey. And stay tuned for the next one where we will get into minerals. Thanks so much for your time and take care.